So we have started our discussion on deadlock avoidance technique, and in this technique we have discussed an algorithm that is, we have said it is Banker's algorithm, which assumes that there are n number of processes and m number of resource types. The algorithm makes use of a number of data structures. One is available, that is a vector of dimension m, which tells you that at a particular instant of time, how many instances of which particular resource type is available. Similarly, we have another data structure which is a matrix max of dimension n by m, which says that what is the maximum requirement of the number of instances of a resource type for a particular process. Similarly, allocation is another matrix of the same dimension n by m, which says that how many instances of which resource type is allocated to which process at a particular instant of time. And similarly, a matrix need, obviously this need matrix can be calculated from max and allocation. So it says that what is the future requirement of the number of instances of different resource types for different processes. Okay. So by making use of these data structures, we have written the Banker's deadlock avoidance algorithm. And there we have said that a process Pi from a particular state, where state is defined by the number of resources available and the resources allocated to different processes, given a particular state, if a process Pi puts a request vector which we call as request I, it's a vector which indicates that the number of instances of different resource types which are requested by processor Pi. So since there are m types of resources, okay, so this request vector will also be of dimension m. Then the algorithm works like this. First you check whether request I is less than or equal to need I, because we have calculated need I from max and allocation, which is the difference between the maximum requirement and the resources which are allocated. So this need I says that what is the future requirement of the process for different resources. Okay. So at no instant of time, request I can be greater than need I, because in that case there is a confliction that whatever the maximum requirement that the process declared earlier, it is exceeding that, which cannot be permitted. Okay. So if request I is less than or equal to need I, that is the request is a permissible request, then only we try to check whether this request can be granted immediately or not. Okay. So then we can have two options, that request I is less than or equal to available, because obviously if request I is greater than available, then the request cannot be granted immediately. The question does not arise. So the process Pi has to wait until and unless further resources are made available by release of the resources by other processes. Okay. So if request I is less than or equal to available, then only we can check whether this request can be immediately granted, or the process Pi will be asked to wait to ascertain that allocation of these resources does not lead the system to an unsafe state. Okay. So if request I is less than or equal to available, then what the system does is, instead of, though the system is in a position to meet this request, but it does not allocate the resources immediately. Rather, it checks whether by this allocation the system will move to an unsafe state or it will remain in a safe state. So if it remains in a safe state, the resources will be allocated. If it moves to an unsafe state, the resources will not be allocated immediately. So that is done in this step, where the system pretends to have allocated the resources by modifying the data structures. The resources are not physically allocated, but the data structures are modified. And that modification is very simple. Available, because if this request is granted, available will be decreased by this much amount. So available is updated to available minus request time. Previously the allocation vector was this much, and if the request is granted, the allocation vector will increase by request time. So allocation is modified to allocation plus request time. And once this request is made, the future need will also be less. So need vector is also modified by need I minus request time. Okay. So by modifying this data structure, now the algorithm moves to a safety algorithm to check whether this new state that has arrived, whether it's a safe state or an unsafe state. So if it is a safe state, then the resource can be allocated. If it is an unsafe state, the resources cannot be allocated immediately. So in safety algorithm, which makes use of two local data structures, work and finish, work is initialized to available. Available comes from the previous part of the algorithm. So this is the available which is allocated to work, and finish is a Boolean vector. All the components of finish are initialized to false. Okay. Then the algorithm works like this. You find a process I for which finish I equal to false and need I is less than or equal to work. You find that work is initialized to available. Okay. So if I get a process for which need I, that is the future requirement, can be met by presently available resources, we assume that that process can be completed in the present state following some sequence. Okay. So because this can be completed, we come to the next step, that is, once this process is complete, then all the resources which are currently allocated to it, they will be released. So work, which is nothing but the available resources, now is incremented by allocation I. Okay, and simultaneously finish I is made to true, indicating that this process can complete. Then go back to step number 2. Okay, now this will have a number of loops. At some point of time, if I find that I cannot get any I for which need I is less than or equal to work, or nor finish I equal to false. Okay, so this may happen by one of the two reasons. Maybe that for all the components of finish I has become equal to true. Okay, so that is one condition. The second case may be that finish I equal to false, but need I is greater than work. Okay, whatever be the case, we come to step number 4. In step number 4, we check that if finish I equal to true for all I, and this is the case when all the processes can complete following some sequence. Okay, then the system is safe. But if finish I is not equal to true, at least for one I, that means that process from the current state cannot finish in any of the sequence. Okay, but that does not mean that physically it will not be able to finish, because maybe in between some process will release some resource, and this process will get the required resources and that will finish. Okay, but if I get that finish I remains false for some process, I'll say that the state is unsafe. And as we said, that unsafe state does not mean that there will be deadlock, but indicates that there can be deadlock. So we never want to take that risk.
So excuse me. So what is this work is equal to work plus allocation? So what are those allocated resources?
The resources allocated to process PI. The ith process for which we are checking, the ith process for which we find that finish I was false and the need I less than 1.
So where are we allocating the resources?
This allocation has been made before. Before coming to this algorithm, this allocation has been made.
The previous.
Previous allocation. Okay. Let us take an example to illustrate this algorithm. Suppose in a system we have got 3 types of resources. We call it the resource type A, resource type B, and resource type C. Okay. I assume that A has got 10 instances of resources, B has 5 instances of the resources, okay, and C has 7 instances of the resources. Okay, so these are the resources that we have in the system. We assume that at a particular instant of time there are 5 processes in the system. Who wants to share these resources? And we name the processes as P0, P1, P2, P3, and P4. So these are the 5 processes who are sharing these resources. At a particular instant of time, we can have a situation like this. Few of these resources will be allocated to different processes, And as we have said that every process has to declare in advance what is its maximum requirement. Okay. So I'll put them in the form of a matrix. Suppose I have allocation max, and here I put available. Okay. Now because there are three resource types A, B and C, so let us have different columns for different resource types. So this column I will use for resource A, resource B, resource C, A, B, C, and similarly for available we will have A, B and C. Okay. So these are the tables that we will make. And we have 5 processes, so I'll put them as P0, P1, P2, P3 and P4. So at a particular instant of time, P1 has been allocated 0 instance of resource A, 1 instance of resource B and 0 instance of resource C, whereas the maximum requirement of the resources for process P0 is something like this: 5, 7, 5 and 3. This is the maximum requirement of the resources for process P0. Similarly, for process P1, let us assume that it will be 2, 0, 0, that is the allocation. For process P2, let us assume this is something like this: 3, 0, 2. For process P3, it may be 2, 1, 1. And for process P4, it may be 0, 0, 2. This is the allocation matrix for different processes. The maximum requirement may be something like this: 7, 5, 3 for process P0, 3, 2, 2 for process P1, 9, 0, 2 for process P2, 2, 2, 2 for process P3, and maybe 4, 3, 3 for process P4. Okay. Now once I know that this is the maximum requirement and this is the allocation, then obviously I can determine that what will be the need. Okay. And to compute the available number of resources, what I have to do is I have to add up all the resources which are allocated to different processes. Okay. So at this particular instant of time, you find that 7 instances of resource type A are allocated to different processes. The maximum number of resources of type A which are available is 10. Out of 10, we have already allocated 7. So in this available, we will have 3 instances of resource type A available. Okay. Similarly, here you have 2 instances of resource type B which are allocated. Maximum number available is 5. So 5 minus 2, we have 3 instances of resource type B that is available. Coming to C, the maximum number of resources is 7, out of which 5 is allocated. So number of instances that is available of resource type C is 2. So this becomes the available vector. Okay. Now to apply Banker's algorithm, we have to find out what is the need matrix. And as we said, that need is simply difference of max and allocation. So let us compute what will be need. The need matrix at this particular instant of time will be something like this, as we have 3 different resource types. So again we will have A, B and C. These are 3 resource types. We have processes P0, P1, P2, P3 and P4. Okay. For P0, you find that maximum requirement is 753, out of which allocated is 010. That means need will be 743. Okay. So for P0, the future need is 7, 4, and 3. Right. Similarly, for P1, maximum requirement is 322, of which allocated is 200. That means future need will be 122. Okay. So for P1, the future need will be 122. Similarly, if you compute, you will find that for P2, the need matrix will be 6, 0, 0. For P3, the need will be 0, 1, 1. And for P4, the need will be 4, 3, 1. Okay. So this is how we compute the need matrix. Now the first task that we have to do is, let us say that we want to find out by some allocation procedure we have come to this state. Okay. And now we want to find out whether the state that we have reached is a safe state or not. That means straightaway we go to Banker's safety algorithm. Okay. In Banker's safety algorithm, what we have done is we have taken data structures, that is work, which is initialized to available, and in this case our available vector is 332. Okay. So work is initialized to 332. Okay. And obviously there is another data structure which is finish, and since there are 5 processes, so this vector finish will also be of dimension 5, and initially all the elements of this finish vector are equal to 0, are equal to false. Okay. Now we want to see whether this state is safe or not. And for Banker's safety algorithm, what we have done, we have taken every process and tried to find out whether the future need of the process can be satisfied by the available number of resources at that instant of time. Okay. Now let us try to see this. We have available number of resources which is 332, and the future need of process P0 is 743. So P0 cannot be completed with these resources at the first go. So finish I for P0 remains equal to false in the first go, but that may be modified later. What about P1? Its future requirement is 122. Okay, so we come to process P1. The future requirement of process P1 is 122. The available number of resources is 332. So you find that 122 is less than or equal to 332 as per definition of the less than or equal to relation over vectors that we have said, that x is less than or equal to y if every component of x is less than or equal to the corresponding component of y, that we have already said. So in this case, you find that need 1, that is the future requirement of process P1, is less than or equal to available number of resources. So P1 can complete operation, and after completion, since P1 can complete operation, so we said that finish I finish of 1 will be equal to true. Okay. And we also make work equal to work plus allocation I. Okay. Now what is allocation I? Allocation I is 200. So our assumption is these resources will be released when P1 is complete. So simply work will be incremented by 200. Okay. That means after this your work vector will be 5, 3, 2. Okay, this is available. Now with this available, I come to P2. For P2, the requirement is 600, which is not less than or equal to this. So P2 cannot complete. Come to P3, the requirement is 011, future requirement, which is less than or equal to this. That condition is true. So I can finish P3 with these available resources. Okay, so I make finish 3 equal to true, and on finish of process P3, work will also be modified. What will be work vector now? Allocated 3 is, you see, allocated 3 is 211. So this 211 will be added to work. Okay, so this will be 7 4 3. Okay, with this I come to P4. In P4 you find that future need is 431, which is less than or equal to this. So P4 can complete. Because P4 can complete, so I make finish 4 equal to true. Okay, and what will be work now? Work will be 7 4 5, because to P4 the number of resources allocated were 002. Okay, so this is the available resources after completion of P4. I'll go back again. You find that future requirement of process P0 is 743. Now it is less than or equal to available resources at this instant of time. Okay, so now P0 can complete, making finish 0 equal to true, okay, and because finish 0 equal to true, the work will also be modified. Now work will become 745 plus the resources allocated to process P0, that is 010. This we have to add to this vector, so work will be 755. Okay, now with this 755 you come to process P2. P1 already complete, P2 could not be completed in the first go. So now we come to process P2, whose future requirement is 600, available resources 755. So now P2 can also complete, making finish 2 equal to true, and work will be modified accordingly. Okay, and what will be work now? Work will be 755 plus allocated 2, that is 302. Okay, so it becomes 10 5 7, and it is quite natural that it will be same as the maximum number of resources that is available in the system. Okay, so you find that in the present state all the processes can complete in sequence, and the sequence is P1 P3 P4 P0 and P2. Okay, and this is the one that we are calling as safe sequence. So safe sequence for this state is, so it is the safe sequence is P1 P3 P4 P0 and P2. This is the safe sequence. Okay, and because a safe sequence exists in the system in this particular state, so the state is safe, right? So you can immediately conclude that the state is safe. Now when I say that safe sequence is 1 3 4 0 P1 P3 P4 P0 and P2, it does not mean that this safe sequence is unique. We have got this step sequence because we have started our scanning from process P0. Instead of starting from process P0, if I move in the reverse order, I start from P4, P3, P2, P1, P0, or I check the processes, scan the processes in any arbitrary order, maybe P2, P0, P1, P3, P4, any arbitrary order. In that case, the algorithm may lead to a different step sequence. So safe sequence in a state is not unique. However, if at least one safe sequence exists in a state, the state is safe. Okay. So there may be multiple number of safe sequences. So what you have to see is whether there is any safe sequence in that state or not. If there is any safe sequence, then the state is safe. Okay. So we have seen that the given state of the system is a safe state. Now, if in this state, because the state is safe, so it is quite likely that the system may reach this state. Once you are in a safe state, if a process now puts a request for some number of resources, okay, so we assume that suppose process P1 has put a request for, so this is request 1, equal to 1, 0. So in the current state, which we have just seen that the current state is a safe state. In the current state, process P1 has put a new request for resources 1, 0, 2. Okay. Now, what we have to see is we have to check whether this request can be granted immediately or not. Okay. So if we want to grant these requests, then we have to again go back to the Banker's algorithm. In the Banker's algorithm, first what we have to do is we have to check whether this request vector of process P1 is less than or equal to need or not. If it is not less than or equal to need, then immediately the request will be aborted. Okay. So you find that you have said that future need of process P1 is 1, 2, 2. Right? It has requested for 1, 0, 2, which is less than or equal to need. That means this request is a valid request. Because it is a valid request, so we have to see whether the request can be granted. For that, the first thing that you have to do is whether it is less than or equal to available. We have seen that the available vector in this case was 332. So 102 is less than or equal to 332. So the system is in a position to allocate these resources. Okay. So it has to check for safety. So first, what Banker's algorithm will do, it will pretend that as if the resources are allocated by modifying the data structures. And the data structures which will be modified are, we said that available, allocation, and need. Okay. So if these resources are allocated, in that case, the available vector will have a new available vector. Let me put it here. The new available vector will be from 332, 102 will be subtracted. Okay. So we will have 2, then 3, 0. Because our available was 332. Okay. This is the request put by process P1. Okay. Which is less than or equal to available. So we assume that the request can be immediately granted. If the request is granted, then the available resources will be 230. Okay. Then the other data structures which will be modified are allocation, and need. Okay. The resources are allocated only to process P1. So only allocation 1 will be changed. others will remain the same. Okay. So coming to that, we find that for process P0, the allocation was 0, 1, 0. We don't change this. For process P1, the allocation was 2, 0, 0. And the additional resources which are allocated now is 1, 0, 2. So we have to add this 1, 0, 2 to 2, 0, 0, which was allocated earlier. Okay. So now for process P1, the allocation vector will be 3, 0, 2. Okay. For process P2, it will remain the same, 3, 0, 2 as before. For process P3, it will remain same as before, 2, 1, 1. For process P4, again it will remain as before, 0, 0, 2. Okay. The other data structure that is modified is need. So in our previous state, the need vector was something like this. For process P0, 7, 4, 3, for P1, 1, 2, 2, for P2, 6, 0, 0, for P3, 0, 1, 1, for P4, 4, 3, 1. Okay. Out of that, P1 has received more number of resources. So the need vector for process P1 will also be modified. Okay. For other processes, need will remain as it is. So for process P0, the need remains as 7, 4, 3. There is no change. For process P1, the need was 1, 2, 2, out of which this is already met. 1, 0, 2 is met. Okay. So need for process P1 will now become 0, 1, 0. 1, 2, 2 was the previous need. Yeah, right. 0, 2, 0. Okay. For others, need will remain the same. For P2, it is still 6, 0, 0. For P3, it is 0, 1, 1. And for P4, it is 4, 3, 1. Okay. So this is the new state that we reach if we allocate these requests, the resources which are requested by process P1. Okay. Now after modification of the state, now what we have to do is, again we have to see whether this new state is safe or not. So for that we have to start the safety algorithm. Okay. And in safety algorithm, what we will do is whether future need of processes can be completed with the help of available resources at that instant. Okay. So again we check. First you see process P0. The future need of process P0 is 743. Okay. Available is 230. So P0 cannot be completed. For process P1, future need is 020. Available is 230. So P1 can complete. After completion, what will be available resources? We have available as 230 and allocated to process P1 is 302. Okay. So available resources will be 5, 3, 2. This is the available number of resources after completion of process P1. Is that okay? Because when I come to process P1, our available number of resources was 230. Okay. Need of process P1 was 020. So this need can be met by these available resources. So process P1 can complete operation. On completion, process P1 will release all these resources which are already allocated to P1. Okay. So available will now be this currently available resources plus the resources which are allocated to process P1. So on completion of process P1, the available resources will be 532. Okay. Come to process P2, future need is 600, which cannot be met. Come to process P3, future need is 011, which is less than or equal to 532. So process P3 can also complete. On completion, the available resources will be, currently available is 532. So it will be 532 plus the resources which are allocated to process P3, that is 211. So the available resources will be 7, 4, 3 after P3 is complete. Future requirement of process P4, 4, 3, 1, which is less than or equal to this. So P4 can also complete. P4, and after completion of P4, the available resources will be, you add to this the resources which are already allocated to process P4. Okay, so available resources will be 7, 4, 6, 3 plus 2, yeah, 5. Okay, so with this, I again go back to process P0. Future need is 743, which is less than this, less than or equal to this. So P0 can also complete. On completion, it will release the resources which are already allocated to P0. So the available resources will be 7, 5, 5. With this, I come to process P2. Future requirement is 600, which can be met with this. So P2 can also complete. And on completion, P2 will release the resources 302 which are already allocated. So available resources after completion of P2 will be 10, 5, 7, and obviously this is same as the maximum number of resources which are available in the system. Okay, and the safe sequence in this case, it happens to be same as before with this scanning, that is P1, P3, P4, P0, and P2. Okay, so this is the safe sequence which can be reached. That means the processes, at least in this order, can complete their operation in the current state. So the state is also safe. And because the state is safe, this request of process P1 can be granted immediately. Okay. However, if we reached any situation that at least one process could not be complete in any sequence, that means the safe sequence does not exist in that particular state. And if the safe sequence does not exist, the request cannot be granted.
So once we get a safe sequence, I don't think there's any need of doing the safety algorithm check again.
Safe sequence we are generating in safety algorithm only.
So the first, for the first time,
Yeah.
when we get a safe sequence,
Yeah.
In the next step, what we are doing is we are subtracting similar amounts from available and
Yeah.
need.
Yeah.
So for that particular process, if need was less than equal to available previously, it will be so
No,
in the
no.
next state also.
Need will be less, but that does not guarantee that you will always get a safe sequence.
So, but when we suppose we start checking from that particular process in the safety check, the need is less than available for that particular process right now also, because both have been subtracted by the same amount. So after this we add the allocation.
Okay.
Allocation I. Now allocation has been added by the same amount which was subtracted.
Okay.
So it reaches the same state. So we will keep on getting the same safe sequence again and again.
No. Not necessary. It may so happen that you don't get a safe sequence at all. That is also possible. You may not get a safe sequence at all, because we are changing the state. This state is not same as before. The state is different from the previous state.
So the state is different, but
Yeah.
after doing these three things, the checking and then adding the allocation,
Yeah.
everything becomes the same.
I don't think so. Why don't you try with some other example? Okay.
Okay.
Say for example, this is the state, and we have seen that this state is safe. Now in the present state, if a process, let us say process P0, process P0 puts a new request of, let us assume 0, 2, 0. you find that 020 is less than available, and 020 is also less than the need of the process. So this is a valid request, and you are in a position to allocate this request, to meet this request. Okay, you take this as an exercise, you try to find out whether this request can be met or not.
So, but you have decided the sequence to be P1, P3, P4, P0, P2. How can
That
you
is
know
safe
which
sequence. That does not mean that this is the sequence in which the processes will be complete. It only says that there is a way in which the processes can complete. But it does not mean that this is the only way in which the processes will be complete. It just says there is a way. But this sequence will change, because at different instant of time, different processes will put different requests. And depending upon which process has put the request, in this case, as I said, that incidentally we have got the same safe sequence. But if the request was made by some other process instead of process P1, okay, it is quite possible that the safe sequence we would have obtained is not this, but it is something else. And safe sequence is not unique. Okay, so you try to see that if P0 puts a request for 020 number of resources in this state, because this state is safe, as we have said, as we have just seen. In the safe state, if P0 puts a request like this, then whether this request can be granted immediately or not. Okay, you try to solve this as an exercise.